let's get started now, folks. So this is lecture 16. And today we're going to cover yet another peripheral in the 328P, and it's the peripheral that gives us a timer or a counter. And we'll use this for making some sounds, for controlling speeds of motor, controlling the brightness of LEDs. I'll also use it for counting external events like reading distances from a sonar. So we're going to use this for a lot of different things. This is a kind of a tricky, sort of complicated lecture to build up. Just sort of, that's just something to be aware of. The topic of counters and timers, this peripheral, is covered in the textbook in 3 different chapters. So it really is kind of spread out. And so if you want to take a look at it, it would be chapter 9, sort of the first part of chapter 9. And then from the get-go, let me just say, as is the case with a lot of the peripherals that we talk about, we're really only going to be using a small piece of what's capable. You know, these microcontrollers can really do a whole lot, but we're just going to really just scratch the surface in how to use the timer counter peripheral. You see these hand-drawn pictures here on the first slide, and I just wanted to show you what it looked like when I was teaching myself the material in this course. So, you know, when I was an undergraduate student way back in the 1980s at UMass, I started out as a computer systems engineer. And after a couple classes where I was doing assembly language programming, I said, there's just too much coding in this, and I switched out of electrical engineering. And so the material that we're talking about here wasn't something that I learned in any detail in, you know, when I was an undergraduate. And then I went out to grad school and did my research. I was doing applied electromagnetics and radar. So getting into positioning myself to be able to teach computer engineering is something I did, you know, a handful of years ago in getting ready to teach this class. And I had used computers in radars for my whole career, but getting down into this level of detail is not something that I had done. So not too long ago, I had my first encounter with these microcontrollers, similar to the way you're having, you know, your first encounter with them now. And so I came across, you know, these diagrams. On the right, there's this architectural drawing that we're always looking at. And then on the left, there's the pin drawing of the Atmega 328P. And so one of the things I decided I have to do is I'm just going to redraw this. Because I find when I get a blank piece of paper and I redraw something, just copying it, when I go through that active exercise of you know, copying something, it helps me sort of understand it, retain it, make sense of it. And so I drew these pictures, and they're the same things that we look at all the time on our slides. But I found it was very valuable to have actually drawn these. And then I carried around with me and looked at them for a long time until they started to become, you know, quite familiar to me. And to this day, the one on the left is one I refer to constantly. I mean, when I'm building something, if I'm writing some code, if I'm preparing a demo for you, I look at that picture several times a day because I don't have all those pins memorized. So I just wanted to sort of put this there for 2 reasons. One, particularly the picture on the left, become familiar with it, you know, post it and hang it somewhere so you can see it, but consider also just drawing it for yourself because, you know, you can see all those different pins on there. Some of them, the ones in yellow, we're used to. Those are the GPIO ports, but a lot of those pins have multiple different functions, and we're going to be starting to make use of the different functions of them. It just helps to get yourself as familiar and as sort of comfortable in remembering some of those things as you can. Okay, so speaking of that architectural drawing, on the left is the one that we've seen many times. And just to review what we've done so far in the course, you know, we started out with GPIO ports, digital pins that we can set high or low. Okay, they're shown in red in the blocks on the lower left. And the code that we used to, to configure those things is the code that's shown, there, just as an example, right? We had to first think of it. You can think about it as initializing the ports by setting the direction registers. We had to do that. You got to determine, do you want this pin to be an input pin or an output pin? Then we set the values of ports, and then we sort of wait. We check to see if pins are high or low, and that told us something about switches that we had in there. But that's how we programmed these ports. Okay, so if you now remember, then there was the UART, right? And in the case of, well, let me back up to the previous slide. This one, by now, I know you're all very familiar with and comfortable with, because you've been doing this so much, GPIO programming. When it came to UART programming, or USART, we use the terms interchangeably, you have not written much of your own code there, because I gave you some functions and said feel free to use them. But you have used a function called UART init, and all I did is we have these first three functions that set up the UART a certain way. And then when you send it characters, we did this. And we just took those things and tucked them away in functions. But you'll notice, if I go to the previous slide, there's sort of a similarity. The symbols are different, but the basic idea, you use a peripheral, you set a couple registers to initialize it, set it up the way you want it, and then you interact with it in your while loop. You start the same way. You set it up with some registers to get it configured the way you want, how many bits, ASCII bits you're using, how many stop bits, whether you use parity bits, the baud rate, you configure all that, and then you move on. And then likewise, when we use the analog to digital converter, similar kind of thing. We set up some initial things, tuck those away in a function called ADC init, but that's sort of setting it up. And then, we kind of interacted with it with some while functions and things like that. And so this is how you interact with all these peripherals. There are some things that you have to do to configure the peripheral the way you want it. And you're setting which pins, maybe you're setting how fast it's doing something. And then quite often you'll take the this gnarly down in the weeds code, tuck that away in a function somewhere and make use of it. But you can sort of see the pattern here now. And so now we're going to introduce yet another peripheral, right? And it's the peripheral of these timer counters. And so they're shown over here. And so you can see what we're gradually doing as time goes by is we're getting to know the various peripherals inside this chip. So what's next? It's going to be the timer counters. There are three of them on there. Timer counter 0, timer counter 1, timer counter 2. And two of them are 8-bit counters and one is a 16-bit counter. So that's where we're going now, okay? So the timer counters on this chip, they function as timers. So what does that mean? They keep time. They keep track of time. And how do they keep track of time? Well, the chip itself doesn't know anything about time. It doesn't know what time it is. It doesn't have its own sense of time. All it does is it counts the number of times it does something. So it counts the number of clock cycles. We tell it how fast our clock is. I mean, we have to configure the chip to take an internal clock or an external clock. We did that with fuses. But once that's done, we have to tell the chip how fast our clock is. And then when we want a delay of a certain amount of time, it uses its knowledge of our clock that we give it. And then it just divides that by a certain number of cycles to generate a time delay. And so these peripherals are, they're a section of the chip that can be set up to create timers based on knowing the speed of the clock that's running the chip. They can also function as counters. So there's a similar thing, a counter and a timer, but you use the same device, but counting is 1, 2, 3, you're counting how many times something happens. And often they're used with external triggers. So you connect something from the outside world to certain pins on the chip, and you set it up as a counter, and it'll count how many times something is happening, in the outside world. How many times is someone pressing a button? How many times is someone breaking a light beam that you might be set up, opening and closing a door or something like that, but just how many times is something happening externally. So that's the notion of timers and counters. Okay, getting into it a little bit, the three counters, they're called timer 0, and you'll notice, in this, you're starting to sort of see this before. There's a lot of tendency to use acronyms like this. This stands for timer, counter, T is timer, C and T is counter, timer counter 0. And then there's also timer counter 1, and then there's also timer counter 2. And those are the names of the registers that keep track of these counts. Timer counter 0 is an 8-bit counter. So what does it mean to have an 8-bit counter? It means it's counting between 0 and 255. That's the idea, because with 8 bits you can count up to 255. The 16-bit counter can count between 0 and 65,535. Okay, and the third counter there, counter 2, is also an 8-bit counter. So that's what we've got in there. And basically, the whole idea behind these things, if we're using them as timers, you're giving it an external clock. In our case, it's 16 megahertz. And you're just telling it to count a certain number of cycles and then let us know when you're done. That's sort of the basic idea. And this is the way that this device can be configured, pretty straightforward, to generate time delays or to generate waveforms of different kinds at different periods. And by using the timer to do it, instead of having to do it all ourselves in a loop, you can use the CPU to go off and do something else. So you configure the timer, you tell it, go do this, and you take care of this. Meanwhile, we're going to be using the processing power to go do something else because we've delegated to this timer peripheral to go off and do the counting. And so let's sort of build that up piecemeal. So think back to ECE 124, okay, which was way back last year, right? A year ago, when you took logic design, and you did some things with counters. And so suppose that I have an 8-bit counter here. So that means it can count between 0, 0, 0, 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1, 1, 1, 1. So we're counting between 0 and 255. And let's assume that the counter has certain features. We can decide that we want to load the counter, preload it with a certain value. All right. And when I give it a clock, right, when we give it a clock, it's going to start counting. And every time I have a rising edge of my clock, it's going to count. So I'm going to supply it a clock, and it's going to count on the rising edge, say, right? Every time the clock goes up, it's going to count up one state. Okay, so that's the idea behind the counter. You give it a clock, it counts, and it also has the capability that we can start it out at any initial value. We can start it out at 0, or we can start it out at 1, or any value. And the way we do that is we preload it with a particular value. So that's the idea. We can set it up as a free running clock, and we can choose to load it with any initial value, and then it'll just start counting. And then what happens when it reaches the top? When it counts, when an 8-bit counter goes all the way up, it counts 249, 250, 251, 252, 253, 254, 255. What happens next? Does it blow up and melt down? No, it goes back to 0. But it often tells you it's going back to 0 by having an overflow, right? So as soon as it reaches 255 and rolls over back to 0 again, it has a bit that goes high that just says, hey, I had an overflow. So that's how this counter works. So in a sense, it's 9 bits. It's 8-bit for the count that we can preload, and then it has also this overflow bit so that you'll know that it has done an overflow, okay? So here's some pseudocode. And what I want to do with this slide and the next is just see how we can use this counter to give us a delay of a certain amount of time. And then we'll use that delay first to turn on an LED for a certain amount of time. and then we'll extend it to cause an LED to blink on and off for a certain amount of time in between. Okay, so we'll start out. This is pseudocode. This is not really C code. It's it's suggestive of code. So the first thing we're going to do is we're going to load the value 0 into the counter. So it's starting out at 0, and then we're going to just tell it to start counting. All right, so that's the only code that we've got here. Load it with 0 and start counting. And so this is what it's going to do. When we say start counting, it means we're supplying it with a clock. It's going to count 0, 1, 2, 3, all the way up. All right, on the rising edge, it's going to count up. It reaches FF, and then it rolls over to 0 again. And when it does that, it raises C out. It tells us the carry or the overflow bit goes high. Okay. Part 2. What I want to do is take what we just talked about and create some pseudocode that we can use to turn on an LED for a certain amount of time. Okay. And so here's how we're going to do that. We're going to start out, we're going to take an LED, we're going to connect it to a pin, and we're going to just make that pin high. We pick any one of our pins, right? And one of our ports, make it high. We're going to load 0 into the counter, and we're going to start the clock. Then we're going to sit there and we're going to wait. We're going to wait until this overflow pin goes high, right? We'll wait till that goes high. We'll stop the clock, and then we'll make the pin low. And so if we do that, what will happen is when we turn on the LED at the beginning of this experiment, we start a clock. It goes 0, 1, 2, 3, 4. Right here, I'm counting in hex, so FE and then FF. Right, that's 255, and then it rolls over to 0. And when it rolls over to 0, that's when that overflow bit goes high. And what I'm doing is here, as I'm waiting until I see that overflow bit go high, then I stop the clock, I disable it, and I make the LED pin go low. So what's happened is that LED pin has been on, and then it goes off. All right. And what we've done is we've just created a crisp, clean delay, a single pulse that has a duration of whatever the clock period is, whatever that happens to be, times 256. Because we started at 0, it went all the way up to 255, that's FF, and then it rolled over. So it went from 0, 255, back to 0, and when it went back to 0, our overflow bit went high. So it counted 256 times T clock. What is T clock? Well, we're going to configure that. And T clock is going to start out with our oscillator. We've got a 16 megahertz oscillator, a pretty fast oscillator driving our chip. T clock, we'll start with that, but we'll see that we have some need to divide it down. Okay, so we've built this little timer here. Now, you could ask, well, what good is an LED that's only on for a short period of time? We like LEDs that blink, say, blinking on and off. That's what we've been seeing so far in the course. So let's just take and modify that code a little bit to create a square wave, because what we want here is to blink an LED on and off at a certain rate. Okay, so here's how we do it. First, we're going to make the LED pin go high. I'm just going to cause that LED to go high. Then we'll get into a loop. We'll load 0 into the counter. So we're starting the counter at 0, and then I start the counter clock. I apply a clock. Now the clock starts counting 0, 1, 2, 3, 4, and so forth, all the way up, FE, FF. And what I'm doing here is I'm waiting until that overflow bit goes to 1. Okay, and that will happen when the clock overflows back to 0. Okay, now at this point, I'm going to set that overflow bit back to 0. That is kind of a design feature. I could call it a quirk or a design feature of the AVR family of chips. When this overflow bit goes high, it will stay high until you set it low with software. So what happens is we're waiting until that bit goes high. It happens right here. That's when C out goes to 1. I have to set it back to 0 in software. Not a big deal. You just have to remember that, right? Then we toggle the LED pin, so it's been on, and then it's off. And then I loop again, and I just do the same thing again. Only this time, since I'm toggling the LED, I'm able to make it go on, off, on, off, on, off. So this is how we can create a blinking LED. Okay, so that's pretty straightforward. And so far, we've used the full 8 bits of the counter. You know, we're starting it with 0, going up to the top, checking the overflow bit, clearing that bit, and then starting again. And so, but we don't have to always start with 0. So one of the things we can do is preload the counter with a value different from 0. And what that'll do is it'll count for a shorter amount of time. That's what we're doing so far is we always preload it with 0. It goes to 1, 2, 3, 4, 5, all the way up to 255. And then it overflows, right? But instead, let's look at what happens if we preload it with a different value. So here, let's start out just building a 4-cycle or a 4-count delay. So all I want to do is I want to count for 4 clock cycles. And then we'll turn this into a square wave. And we'll say, okay, we know how to make a square wave that'll count 4 cycles or 256. Well, we actually know how to make one that'll count anything in between. But let's just look at how we would, if we only wanted to count 4 clock cycles, we'd start out by loading 0xFC into the counter. Now, why is that? Well, I put in 0xFE. I want to start with that. Okay, I'm going to first load 0xFC very deliberately into the counter. Then I'm going to start the counter clock. So I load that value in, and then I tell it to start counting. So it's got 0xFC. After 1 cycle, it's 0xFD. It's counting in hex. 0xFE, 0xFF, and then it rolls over again to 0x00. See, what I've done is I preloaded it four steps down from the top. And once I preload it there, then I apply the clock, I let it start counting, and it quickly sort of crashes into the top and rolls over and sets that overflow bit. So the next part of this, how could we turn on an LED precisely for 4 clock cycles? Well, we make the LED pin high, we load 0xFC into the counter, start the clock, wait for the overflow, stop the clock, and then we make our pin low. Okay, and what I've done over here is I've just showed you the count. You know, where if we were counting, if we were preloading with 0, we would start 0, 1, 2, and all the way up. But instead, we're preloading it with 0xFC, which is 252. So it goes 252, 253, 254, 255, and back to 0. Okay, and in between we have 1 clock, 2 clocks, 3 clocks, 4 clocks. Okay, so that's the idea. If we use this pseudocode, we would turn on an LED, we'd preload it, start it counting, wait for the overflow, and then shut off the LED. All right, let's turn that into a square wave now. So that the LED is on, off, and so forth. Okay, I've got a question here in the chat. What happens if you don't preload a value? It will I would expect it to default to 0 if you don't preload a value. So if we let me answer this code here to complete this one, and then we'll look at what happens if we don't load the counter. So in this particular code, what I want to do is have some pseudocode that'll cause an LED to blink on and off every 8 cycles. Meaning, in 8 cycles, I want it to have been on and then off. So it's on for 4 and off for 4. So we first make the LED pin high, right? That's right here. We make that pin high. I load 0xFC into the counter, and I start the counter clock. So here's when I'm loading it. And after 1 clock cycle, it's at here. After another cycle, we reach the top, we roll over, right? We set our overflow bit, and I'm waiting for that. Then I'm setting that overflow bit back to 0, and I'm toggling the LED. I'm bringing it down. Then we're going through the loop again. So I'm preloading the counter, right? Back 4 steps below the top, and we're doing it all again. But this time the LED is off. And I just repeat this whole thing. Okay. So what would happen if we didn't load the counter here? That's what would happen there. Well, I will need to double check this, but my expectation is when you first power up, that register is going to be at 0. And so it's going to default to 0 here. So you'll start the clock. You'll just wait for the overflow to happen. You'll toggle. So I would expect, if you don't load a value, I would expect it to keep on counting from 0 to 255. But that's something I would want to double check, that that's the default. Okay, so but look at what we've done here. We've looked at how we can count clock cycles, and we've looked at some pseudocode that we can use to use this in the way we're doing it by toggling a pin. We can make square waves, and we can make square waves sort of any frequency we want. Now, what do we mean by any frequency we want? Well, based on the size of our clock, the speed of our clock, we can make waves of 1 clock cycle up to 250. Well, we can count anywhere between 0 and 255, right? So there are 256 states that we can count with this. To get more variability with that, we would have to divide down the clock, and I'm going to show you that. Here, by the way, just if we take and just sort of generalize what we just did, this on this slide. On this slide, we have slide 10. I'm showing you specifically what happens if we preload it 4 sort of steps from the top, right? It's because 256 minus 212 is 4. We preloaded it with 212, which corresponded to FC in hex. And so the basic idea is, if you want to have it count n cycles, you just load it, 256 minus n. And so this slide just sort of shows you how you could go ahead and program it to count n times t clock cycles. So it's just the generalization of what we just talked about. Okay, so I've got a question. What happens if, does C count equal 1 prevent the counter from counting further? No, if we don't do this, if we don't set C out back to 0, it doesn't freeze the counter. The counter will keep on going as long as you have a clock. And so, we once we started a counter clock, as long as we continue to provide it with a clock, it'll keep on counting. But if we didn't do this, if we crossed out this line, then what would happen here, after we go through this loop the first time, we'd come back to it again, and we're trying to wait until the overflow is 1. So what would happen is it would immediately be set to 1, so we wouldn't wait. So our timing would be messed up. So the first time we go through the loop, it would work correctly. But the next time, we would just pass right through the loop without waiting at all. So that's why with every time through the loop, we want to reset that overflow counter. Okay, so with that kind of as background, now let's sort of take that idea and the pseudocode, and let's look at how we can implement that on our chip. So I'm going to start out by showing you how Microchip describes the timer counter peripheral 0 in its documentation. And so this is the way it's described both in the data sheet and also in the textbook. So there's an 8-bit register. It's timer counter 0. And so it uses the language TCNT0. There's also TCNT1 for counter 1 and TCNT2 for counter 2. So timer counter register 0. And what you do is, if you want to preload it, you just write a value to this. If you want to see what its value is, you just read from this register. Okay, so that's the first part. Then that overflow bit that we were looking at is called TOV01. That's the timer overflow flag. Okay, the language here, look at the acronym. So the first one, timer counter 0, because there are 3 of them in there. Numbers 0, 1, and 2. Timer overflow flag, timer overflow, and then we're using counter number 0. This is one bit in a register somewhere that we'll have to keep track of. And I'll show you what that register is called. Okay, here it is down here. There is an 8-bit register called TIFR0. That stands for Timer Interrupt Flag Register. And we're just interested in looking at bit 1 of it. And so when we want to find out, has this overflow occurred, we just keep looking at that bit to make sure it has gone high. And that's the one that we set back to 0 every time. Okay, what else? There are 2 registers that are used to configure the timers, and there's lots of configurability, as I'll show you. There's TCCR0A, that's Timer Counter Control Register A. That's an 8-bit register, and Timer Counter Control Register B. So this is sort of the basics. And what we're going to be doing is we'll preload into this one. We'll wait for this bit to go high. And then these other things are what we use to enable the clock and to describe whether we want it to count up, count down, or do other things. What I've just shown you is a simplified view of this timer counter. On the next slide, I'm just going to show you kind of the full-up version of it with more registers. Okay. Oh, by the way, before I do, these registers, these TCCR0A, they're just shown here. They have a lot of bits in them, and the ones that are going to matter to us are going to be these 3, which set the counting mode, and also these, which are going to be clock select. We're going to ignore the others for now, but we'll get into them a little bit on Monday of next week. This is the simplified view. Here's the more complicated view. There are even more registers associated with this clock, and there's lots of different capability. There's the output compare register, and we're going to actually make use of that more on Monday. So for now, let's sort of ignore this part of it, and we're going to focus on this. And so what we're going to expect to see is code that sort of uses these 2 registers here to configure this counter the right way. We'll tell it the mode we want it to operate. We'll tell it how fast the clock should be. We'll load an initial value in here, and then we'll be waiting for this to overflow. Okay, so that's where we're going. Now let's take a look at these registers. I'm going to back it up. I'll try not to make you seasick, but we're just these things that I circled in red. I want to dig into that a little bit. So these are the timer counter control registers. You got to set them the right way so the counter will do what you want it to do. So there are 2 of those registers, and this first timer, it has 7 different modes to it. It has what's called normal mode, which just means it counts up in the way we've just been describing. So the sort of pseudocode that I just showed you, that corresponds to normal mode. There are actually six other modes here. One of them is one state is reserved; it's not used. On Monday, we're gonna talk about PWM, fast PWM, phase correct PWM. We'll talk about those on Monday. But for right now, all we want to do is use the normal mode. And so the way the mode gets configured, you tell this counter which mode you want by specifying these 3 bits, WGM 02, 01, and 00. And they happen to be spread across 2 different registers. Now, I can't tell you why they're spread across 2 different registers, but when someone is designing a microcontroller like this, you're designing an entire system, and it has all kinds of functions and capabilities associated with it. And I think what they tend to do is sort of cram the bits in where you can fit them in. I mean, there's probably more of a systems concept to that. But when I'm looking at how to program this, I sometimes find, all right, it's a little strange. If I have to set something like this, I have to actually set 3 bits across 2 different registers. But okay, I can live with that. If I want it to be a normal mode, I'm just going to put a 0 here, and I'm going to put a 0 here, and a 0 here. Okay, fine. Once I learn that. Okay, so that'll set it as a normal mode. Then there's also the business of the clock and the prescaler. So now here's the situation with that. We're running with a 16 megahertz clock. So that means the clock cycle is 16 million cycles per second. And so this 8-bit counter can only count from 0 to 255. So let's suppose we have it counting the full range, right? Then it takes, if you load it with 0, you're going to get your overflow 256 clock cycles later. What's the maximum delay that we can make with our, when we're using our 16 megahertz clock? Well, if you take 16, if that's, if every time this thing ticks, it's 1/16 of a microsecond, right? And that's what that corresponds to. And if it counts up to 256, then let's see what that delay would be. Give me a second, I'll get my calculator. 16 megahertz, let's see, 16 megahertz. That corresponds to a delay of 0.0000006 seconds. And then if I multiply that by 256, that means that the maximum delay that we can get is 0.0000016. Right? That looks like, if I've done it right, it's 16 microseconds. Now, things that happen on human scales take much longer than that, right? When we want LEDs to blink, you can't see an LED blinking faster than 10 hertz, right? Actually, more like 20 to 30 hertz. But if you have something blinking at 100 hertz, with a delay of less than 10 milliseconds, you can't see it. If you're generating sound, if you get up above a few kilohertz, you can't see that. If you're using this thing to keep track of how many people walk through a door and all that, most of the stuff that you use on human scales, you need to count time on, tenths of a second, maybe hundredths of a second, or up to tens or hundreds of a second. So our 16 megahertz clock is really happening sort of way too fast for human scales. So what you need to do is divide down the clock, and that's what's being shown here. So the idea is we take that 16 megahertz clock, and it goes into what's called a 10-bit prescaler, right? So 10 bits, if you're counting an additional 10 bits, you can count up to 1024. So what you can do is you can divide that clock by 1024, or by 256, or 64, or 8, or you can take the clock directly. The idea here is you can choose as the time base for this counter either your clock directly, or an 1/8 of the clock speed, or a 64th, or 256, or 1024. So you can really divide it down if you need to. And the important thing here is what you want to do is get the clock speed down so that it is now on a scale that is relevant to whatever the situation is that you're sort of interacting with, human scales, or the scale of a hummingbird, or whatever, right? So before I leave this slide and show you how to configure it even further, I just want to make this point. 16 megahertz is a fast clock, as we just described. It does 16 million cycles in a second. That's a lot. If your laptop were running at that speed, it would be completely useless, right? What's the speed of the clock in your laptop? It's in the gigahertz range, right? It's several gigahertz. So it's thousands of times faster than this. So even when we say 16 megahertz is a fast clock, it's fast from the point of view of you and me and what our eyes can see and what our ears can hear and the speed of sound and things like that. But it's very, very slow when you consider the need to run algorithms really fast to do AI or something like that, okay? So I don't want to leave you with the impression that 16 megahertz is a fast clock and end it there. It's actually a very slow clock for a computer. But when we make a an embedded computer, and we use it in a pacemaker, or we're using it to count how many hummingbirds are going into our bird feeder, or how many people are crossing a light beam, we're doing things on a much slower scale, and so it's necessary to slow down the clock. Okay. But the idea here is you've got a multiplexer, and you have your clock, in our case 16 megahertz, and you have available all of these different taps from this prescaler counter, and you choose which one you want. And you can see that there are, well, it actually shows eight different possibilities here. You actually select them with one of these three pins, clock select pin, and those correspond to these 3 bits here: CS0, CS1, and CS2. And so just to walk through those, if you set those all at 0, you will have no clock. That means you're disabling the clock. So when you set these 3 at 0, there's no clock, the thing isn't running. When you set them at 1, then you're taking your external clock directly, so it's running at 16 megahertz. If you set it at 2, it would be running at 2 megahertz, and so forth. Now, you may notice, gee, there are actually, yeah, let me leave it at that. There's actually over here, there's sort of 2 additional possibilities where instead of using the internal clock, you're using an external event trigger, and we're going to take care of that in about 2 weeks from now. So the point behind this messy slide, there are 8 possibilities. You select them with 3 different pins, because 2 to the 3rd is 8. If you go with 0, there's no clock. If you go with 1 through 5, you're selecting a divided down version of the main system clock. And if you go with the upper 2 bits, you're using an external event trigger. More on that later. So let's just show, and let's just take everything we just described and sort of wrap it up sort of nicely here. Clock selector, and these are the options. Okay. And I'm going to show you some examples now where we make use of some of these clock dividers. And so the application that I want to develop here is, let's write a program to create a 1 kilohertz square wave, and let's apply that to the little piezoelectric speaker that you have in your kit. Okay, so a piezoelectric speaker is like the speaker you have in your cell phone. It's like a speaker you have in a lot of devices. It's a tiny little speaker. And so what we want to do is use it to create a 1 kilohertz tone that we would hear. I mean, we'll hear that as 1 kilohertz. Okay, so let's just spend a minute to talk about how a piezoelectric speaker works. So what's inside there is a piece of piezoelectric material. It's a kind of a crystal, flat piece of material. And if you just take it and normally there's no voltage across it. You just have that flat material, no voltage across it, and it's flat. If you take and you apply a positive voltage across that crystal, from one end to the other, what it's going to do is it's going to cause some material strain in the crystal, and you're going to cause it to actually deflect, right? And I'm exaggerating what happens, but the idea is it's going to kind of bend. It's going to contract in one direction. And so you can think about it as creating sort of an outward bulge to that crystal. And then if you were to reverse the polarity of that voltage, it's going to create a strain in the opposite direction. And so it's going to create sort of an inward bulge. Okay. And you can actually hear this. If you were to take a battery and connect it to your crystal, you'll just hear it sort of go click. And you're actually hearing this piece of crystal sort of bending. Okay, how do we use that to make sound? Well, what we're going to do is, instead of just having a voltage that's positive and a voltage that's negative, we're going to create a square wave like we've been talking about. Okay, and every time that square wave is positive, it's going to be sort of bulging out. And every time that square wave is negative, it's going to be going in that direction. So we're going to be causing this crystal to sort of bow out and then in, out and in, out and in. And every time it does that, it creates a little pressure change in the air. It's creating a little puff of air, a pressure differential. And that manifests as sound. And so if you take that thing and you put it next to your ear, right, you will be able to hear that, because this, if you take air and you move it back and forth at a certain frequency, that's how you create sound. And what actually happens is that pressure variation travels into your ear. And depending on the frequency, there's actually a different wavelength associated with it. And by wavelength, I mean, you sort of you've been looking at this in your in your classes last semester, the idea of wavelength a little bit, but you can also think about, if you throw a rock out on the ocean and you see or on a pond, you see the concentric rings of waves, and you look at the spacing between those crests. That's the wavelength. And what happens is, depending on the frequency, there's a different wavelength. And then depending on the wavelength, what the wave does is it'll actually travel into your ear, and you have this curved bone in there, the cochlea, and that actually gets tickled at a different part of your ear, depending on the wavelength. And your ear geniusly perceives that as a sound of a different pitch. And so we're able to hear things between about 20 hertz and 20 kilohertz. And as time goes by, as you get older, this low end kind of goes up and this high end goes down, right? And that's a combination of listening to loud rock music and aging and other environmental effects, right? But you can use this little piezoelectric crystal, and we can create a square wave at a certain frequency. And because of everything we just talked about, the way it tickles your ear, as long as it's in this range, you'll hear it. You'll say, aha, I recognize that as 1 kilohertz. So let's do that now. So we're going to create a program using this timer to create a 1 kilohertz square wave applied to the piezoelectric speaker. And we're going to use timer 0 in normal mode, counting up the way we just described. And I've pre-calculated that we're going to use the 1/64th prescaler. By that, what I mean is we've got our external clock, 16 megahertz. We're going to first divide that down by 64, and then we're going to apply that to this counter. And so what we want to do is create this waveform here. Okay, it's going to be a square wave. Now, a sine wave sounds better than a square wave, and the reason is that if you listen to a sine wave, you'll hear a pure monochromatic waveform. If you listen to a square wave, it actually has something called harmonics in it. And so this square wave, it sort of will sound like a dirty 1 kilohertz tone because it has various odd harmonics associated with it, but that's okay. What we want to do is we want it to be 1 kilohertz, which means that we want the period of this wave to be 1 millisecond, because 1 millisecond is the reciprocal of a kilohertz. And with our fast clock, we really tend to count in microseconds. A millisecond is 1,000th of a second, a microsecond is 1,000,000th. So what we want is a waveform that's 1,000 microseconds wide. We're going to be toggling this piezoelectric crystal, right? The way, instead of toggling an LED, we're going to toggle the crystal, meaning we're going to give it when it's high, we're going to have our output pin is going to be high, and then the output pin is going to be low, and that's going to be causing this sort of back and forth strain in the crystal. So we're just toggling this thing. So what that means is that we're going to set up our counter to count 500 milliseconds, toggle, count another microseconds, right? Toggle, count 500 microseconds, toggle, and so forth. So we need to our job now in coding is to build a counter that'll count up 500 microseconds, and then we'll toggle. So here's our pseudocode over here on the left. Okay, we're going to choose which bit we want, which GPIO bit we want, and we'll hook that up directly to the piezo speaker, because that piezo speaker will happily take a TTL square wave 0 to 5 volts, and that's what's going to come out of our GPIO. So we'll set that as an output bit. We'll preload the counter, okay, and we have to figure out what that preload value is going to be. We'll set it in operating mode. It looks like I counted twice here. It should be 1, 2, 3, 4, 5, 6. So a little typo there. But we preload the counter. We tell it to count up in normal mode. We tell it to start a clock, and the clock is going to be 1/64th of our system clock. And I'll tell you why in just a minute. We'll wait for the counter to overflow. Then we'll toggle the GPIO bit, and we'll have to clear the overflow bit, and we'll cycle again. So it's the same thing that we just talked about. Let's just take a look over here and figure out how to preload it. So what we want is a 1 kilohertz square wave, which means a 1 millisecond period. which means that we want a delay of 500 microseconds, which is what we just talked about here. So how do we get a delay of 500 microseconds? Well, our clock, it has an oscillator of 16 megahertz. That means the period associated with that oscillator, the time from rising edge to rising edge of that oscillator is 1 over the frequency. It's 0.0625 microseconds, pretty tiny, okay? It's 62.5 nanoseconds. It's pretty tiny, it's a fraction of a microsecond. But we're using a prescaler of 1 to 64, which means we're going to pre-divide that by a factor of 64. So it's going to take 64 of our system clocks to cause 1 clock in our counter. So that means our clock is going to be counting, and the period of it, each cycle, is going to be 64 times that system clock, or 4 microseconds. Okay, so you have to kind of keep track of a lot of this stuff in here. All right, so now we know we want our counter to give us a total delay of 4 microseconds. So I'm sorry, I take that back. We want it to have a total delay of 500 microseconds. But the way we're using this 1 to 64 prescaler, each cycle is going to take 4 microseconds. So we want a delay of 500. Each one's going to be 4. That means we want the counter to count 125. Danny, we're using so I have a question here. Let me come back to it. I'll finish this up and then come back to it. We wanted to count 125 cycles. And so now remember the way this thing counts. We first preload it, and we want to preload it 125 cycles from the top. So the top is 256. I want to preload it 125 below that. So I'm going to preload it with 131. So to back it all up, we're going to go into a loop. I'm going to set that output pin high. I'm going to preload the counter with 131. I'm going to enable it, tell it to start counting. I'll wait for the overflow bit. Then I'll clear the overflow bit. I'll toggle, and then I'll go back up and do it all again. So the question is, why are we using a prescaler? We're using a prescaler because our system clock is just too fast. See, that system clock is 16 megahertz. Each period of that clock is 0.0625 microseconds. And I need to create a 500 microsecond waveform. The maximum delay I can get out of that clock is going to be 256 times 0.0625 microseconds. So let me see what that is. 0.0625 microseconds. If I multiply that by 256, it's 16. So the biggest delay I can get out of this 8-bit counter is 16 microseconds. And that's if I let it count all the way from 0 to the top. But I want a 500 microsecond delay. So I have to slow down the clock. And so that's what the prescaler does. And we have a variety of options for the prescaler. So I said, let me try 64. So I have my 16 megahertz clock. I pre-divide it by 64. That gives me 4 microseconds for every period of it. And then I just have to count 125 of those. So if I sort of put all that together here, I have to preload the counter. And I want it to be 125 ticks away from the top, so I have to preload it with 131. And this is a case where I find it handy to actually put a value in decimal. You can do it in hex, but I tend to find it's helpful in decimal because we're subtracting it from 256. So we're going to preload it with 131. And then we have to specify these registers. We want it to be in normal mode, right? Which means we want a 0 here, a 0 here, and a 0 here. And we also wanted, I think I have it over here, we wanted to pre-divide that clock by 64. And so that's option 3. So I have to have these counting up to 3. So that's 0, 1, 1, 0, 1, 1. So if I pull all that together, what I have to do is I have to preload the counter here. And then these two lines will enable the clock with a divide by 64 counter in normal mode. Okay, so that's it. And we're going to take that and embed that in some code now. Okay, here it is. So this is the code that'll do it. This comment describes everything we just did. We just talked about. It sort of has the math associated with it, and I won't go through that here. But let me just show you what's happening here in the code. We're going to first set up. I'm using bit PB0, so I'm just setting that up as an output bit. Then we have our while loop. I'm going to preload the counter. It's 100 and what did we say? It was 125 steps away from the top. I'm going to initialize those registers. I'm going to wait for it to overflow. I stop the clock, clear the counter, toggle the output pin, and then loop again. Okay. And here's the circuit. And the circuit is everything that we left with on Monday. On Monday, we put an LED on there. I'm not using the LED, but I just kept it on there. But what I've done is I've added this speaker. And the speaker is on PB0, which is just this pin right here. Okay. And so that pin is actually corresponds to this pin right here. It's these piezoelectric speakers are kind of tricky because they have sort of short little pins. When you put it onto the board, you have to sort of look underneath to see where the pin is. But one of the pins is going here, and then the other pin is just going to ground. So when I run this, you're going to hear a 1 kilohertz tone.
Professor, that's a little bit hard to hear. It might not be picked up by your mic.
Okay, let me see if I can do it again. Turn the mic around. Can you hear that now?
Cutting in and out, but yes.
All right, let's try. How about if I try this? Different setting on the mic.
It sounds like what's happening is it registers it initially as a sound, and then it cuts it out as background noise once it's consistent.
Cuts it out as background noise. Okay. I'm noticing sort of many things as a result of Zooming. And you may have noticed this, when I make what should be a blink-free display with the 4-digit 7-segment display, and then I film it with the camera on Zoom, you actually see it flickering, and that's because of the effective film rate from the Zoom camera. And so here we have the issue of what's happening to the sound over Zoom. Okay, what I want to do on the very next slide here is just show you some code. I won't go through it. I'll just show you the code. You can experiment with it on your own. But what I wanted to do is just make a sequence of 4 tones. And they all should be within our range of hearing: 62.5 hertz, 250 hertz, 1 kilohertz, and 4 kilohertz. And so to do this, I'm kind of walking through and I'm choosing different prescalers. So the code's a little more complicated, but when I run it, you should hear it sequencing through 4 tones. And so let's see if I can do that. Maybe I even turn up the gain on this microphone. I'll try that. All right, I'm going to run this. All right, did you hear 4 tones there?
Yes.
Okay, so now when you start doing this experimenting, this is guaranteed to bother your roommates, anyone in your house, anyone who can hear it, right? And they'll come down and say, what is that noise? That always happens to me when I'm preparing these things, that my wife and daughters always come down and complain about it. I'm not actually going to ask you to build any of these tones for homework, but you may want to experiment with these. Go ahead and build these things on your own, just using the code here and the circuit, just to help you sort of make sense of this. I'm about almost finished here. I just wanted to show you the difference between the different timers. And so we'll do that with a little bit of, I'll sort of drown you in some PowerPoint. There are 3 timers, timer 0 and 2. They're both 8-bit timers, so they both look alike, right? Everything we talked about for timer 0 just about also applies for timer 2. The difference is, whereas on timer 1, you can give it an external clock so it can count events, but on timer 2, it has more options for the prescaler. So that's the difference. It has sort of a finer degree of prescaling. And I just tell you that, in case you're in a situation, you could well be when you do senior design project where you're looking for multiple timers, you have those two 8-bit timers. There's also timer 1, which is a 64-bit timer. Much of it's the same, but since it's a 16-bit timer. Since it's 16 bits, it actually has two 8-bit registers that comprise the timer. And it has some more complexity to it. It has a whole bunch of operating modes. We're going to cover that a little bit toward the very end of the semester. Okay, that's it for now. Let's see. Don't get too worked up on the timers right now, but do, if you haven't yet, go ahead and replicate what we did in class on Monday. That's the important thing, because you want to make sure you're able to configure and program the chip, because we're going to, on this coming Monday, we'll take some of this stuff we talked about with the timer and then add that with a bare chip on a board and add some more to it and use it to control a motor. Okay. Let's see. I have a question here. How would you do what we're doing if we want to generate the tone without making the entire microcontroller stop at the delay on line 22? That's an outstanding question. And so you'll notice that in much of what we've been doing here, when we use the analog to digital converter, and also when we're doing this, we're waiting for something to happen. We're sitting there waiting for the thing to be done. We waited for the UART to be done. We wait for the analog to digital converter to be done, and now we're waiting for a timer to be done. If the UART's fast, the ADD converter is fast, the timers can be long. So Sebastian's asked an excellent question. If we have a long timer and we're just sitting there waiting for it to overflow, we're tying up our processor. What we've been doing is polling. You call that polling. You're polling a bit. Instead, we're going to introduce interrupts, and we're going to do that after we talk about motors. But when you use interrupt programming, you set it up so that it all happens in the background, and that way you can use your most of the resources in the microprocessor for something else, and you all have all this stuff happening in the background with interrupts. And so we'll get to that after we finish up with motors. So that's it for now. Happy to take any questions you might have.